So, we are on to lecture 20th, and we are discussing steel making reactions. And the last reaction and perhaps one of the most significant reactions in steel making that we want to discuss is the phosphorus reaction, which we also call dephosphorization. The statement is contextual, dephosphorization or phosphorus reaction. So, these terminologies are used with reference to steel making. Dephosphorization, that means what we are talking about is the removal of phosphorus from the hot metal, and as we have seen that in blast furnace we can have almost all the phosphorus which are present in the charged material will get reduced or likely to get reduced, and the reduced phosphorus as a consequence will join the metal phase. So, therefore, the hot metal will contain perhaps every bit of phosphorus that is there in the charged material, and the hot metal therefore can, as I have indicated, depending on the ore chemistry, whether you are using a high phosphorus grade iron ore or a low phosphorus grade, blast furnace hot metal typically would contain 0.5 weight percentage or 0.1 weight percentage of phosphorus. That is the kind of phosphorus that we are expecting in the melt, and we are targeting a phosphorus. The target phosphorus in the final finished product could be as low as 10 ppm, or I think in general about 30 ppm phosphorus of good steel, not suitable for all applications, but a good steel produced by primary and secondary steel making for some critical applications should contain max 30 ppm phosphorus and so on. So, quite a bit of phosphorus is therefore required to be eliminated during oxidizing refining, and this removal or elimination of phosphorus is termed as the dephosphorization, and we also write it in short form like DEP. And similarly, in the context of sulfur also I said desulfurization or sulfur reactions, and we could have written there D dash-hyphen capital S. So, the melt contains phosphorus, and this phosphorus, if we write a balanced equation, dissolved oxygen, and then we have a basic environment, and then we get 2PO4 3 minus. That is what basically is the phosphorus reaction in steel making. In molecular form, one writes typically phosphorus plus oxygen plus calcium oxide 3CO, and then we will write here 2 CO calcium phosphate CaO PO4 3 or CaPO4 3, that is what Ca3 calcium phosphate Ca3 PO4 2, that is what it is if you write instead of calcium oxide here, and that is what we will write phosphorus plus oxygen plus calcium oxide is equal to calcium phosphate in molecular form. And the equilibrium constant assuming, so these are in metal phase, these are in slag phases. So, what we are talking about equilibrium, when we talk about chemical equilibrium, we are essentially now talking about slag metal equilibrium. Should there be slag metal equilibrium, and then we can say with respect to phosphorus and oxygen content, then we can write down the K equilibrium constant is equal to activity of phosphate ion PO4 3 minus in the slag raised to the power 2, and then we have here, and if you use with percentage scale, and then you have Henryan activity of phosphorus in the metal, Henryan activity of, and this is squared, of oxygen, and then we have activity of oxygen and ion in the, and this is 3. So, we have cubed, that is what is the. You can visualize this reaction, for example, in terms of this is the concentration of phosphate in the slag phase. So, it is a measure of phosphorus which is there in the slag phase at equilibrium, and This one also similarly Hp, Henrian activity of phosphorus or activity of phosphorus here, is also a measure of what percentage of phosphorus in the metal phase, because we can write it always in terms of an activity. We can say that it is, if you are using 1 weight percentage scale, standard state is 1 weight percentage, that is what we define, then we can write this activity is equal to the weight percentage of phosphorus, or alternatively we can write it in terms of weight percentage of phosphorus multiplied by activity coefficient. Whichever way you write, so this term, this and this, they can be interpreted, the ratio of the two terms can be interpreted as a ratio between phosphorus content in the slag divided by the phosphorus content in the metal phase, and that we see that this ratio can be expressed in will be equal to K equilibrium multiplied by HO to the power 5 Henrian activity to the oxygen, dissolved oxygen in the melt to the power 5 N activity. And what it indicates, that what we want to do in phosphorus removal is we want to get this ratio, which is a measure of weight percentage of phosphorus in the slag, not exactly equal, but it is a measure as I said, okay, because these activities may not be equal to the weight percentage or mole fractions. So, since this is a measure of phosphorus in the slag divided by phosphorus in the metal, so therefore, it is understood this ratio, which is also some sort of a equilibrium partition coefficient, is going to be maximum provided the equilibrium constant value assumes a very high value, provided, because these are all going to go to this side, okay. And then we see that for this ratio, whatever is there here, for this ratio to assume a very large value, which essentially indicates a large phosphorus partition coefficient in terms of our definition, that is L sub p E, which is equal to weight percent phosphorus in slag divided by weight percentage phosphorus in metal. Okay. So, in order to get a large partition coefficient, equilibrium partition coefficient, it is understood that equilibrium constant value has to be large, HO value has to be large, and this value also activity or the basicity, this is the measure of the basicity of the slag, and the basicity of the slag is also going to be. So, what we see that the equilibrium constant, the activity of oxygen and the activity of calcium oxide in the slag are important parameters, and this also tells us that larger is the oxygen concentration, more will be the tendency shift the equilibrium towards a higher phosphorus in the slag phase. This equation also tells us that larger is the concentration of the basic oxides in the slag, this the equilibrium of this reaction will be shifted towards a higher value of phosphite ion in the slag phase. So, a high oxygen potential of the melt, and we also say that where high oxygen potential of the melt is what? It is synonymous to high activity of oxygen, because we are talking of slag metal reactions, that is why we have written equilibrium. And if there is a likelihood, very likely, quite a bit of likelihood that this oxygen content of the metal is going to be in equilibrium with a corresponding amount of FeO in the slag. So, these are synonymous. So, when you say, I can say that oxygen content of the melt is very, very high, or I can also use the term that the oxygen potential in the slag is very high. Okay? They are one and the same thing. So, in an oxidizing environment, obviously the FeO content of the slag is going to be larger. In an oxidizing environment, in a basic environment, there is going to be a great chance of phosphorus elimination, or this reaction to go from left to right. And this reaction, as I have written, is an exothermic reaction. So, therefore, relatively low temperature is going to be favored as far as the equilibrium constant will assume a high value, provided you use somewhat lower temperature, because this reaction is an exothermic reaction. So, what we find out from this simple set of statements, that a higher phosphorus partition coefficient will result, provided we have an oxidizing environment which is representative of high FeO and high oxygen content, provided we have a high basic oxide in the slag or high basicity of the slag, and then we have relatively lower temperature. These three conditions are. So, three different factors, as I was telling, that oxygen potential, which I have just now mentioned, high basicity of the slag and low relatively lower temperature, that is going to facilitate a dephosphorization reaction, and these are the three phosphorus essential conditions which ensure phosphorus removal. And all these conditions barring the end period or the time carbon is completely driven out, are satisfied during the steel making process. And if you now compare desulfurization with dephosphorylation, you will see that in desulfurization, what we said, we require a basic slag, but we require a reducing environment. Okay? So therefore, the objectives are quite opposite as far as desulfurization and dephosphorylation is concerned, and that is why I have been repeatedly saying that sulfur removal is facilitated in blast furnace. On the other hand, phosphorus removal is facilitated in steel making. Also, we must understand, in blast furnace we are constrained about using a very high basicity. On the other hand, in steel making we have no problem, because we have extra heat generated because of oxidation of carbon to carbon monoxide, because of oxidation of silicon to silicon dioxide. Okay? And all these metalloid reduction oxidation reaction gives rise to or yields enormous amount of heat, and therefore we can add a very good amount of lime into the system, resulting or yielding a basicity of the slag or a V ratio which can often approach a value of 4 or so. So this high basicity value, which is present together with the intense oxidizing environment, facilitates phosphorus removal to a large extent. Only issue is here that towards the end of the process, when, as you have indicated, that I have said yesterday or in the preceding lectures, that as the carbon content goes down and down with the progress of the blow, the slag iron oxide content increases. And also towards this later phase, what happens is the bath temperature develops quite rapidly, because iron to oxygen reaction, large scale oxidation of iron really gives rise to iron oxide, gives rise to or yields a huge amount of temperature, and the melt temperature very rapidly increases. And because this reaction is exothermic in nature, so the higher temperature which happens towards the later part of the blow, okay, can cause this reaction, the phosphate ions to dissociate and these reactions to go in the reverse reaction, and this is called the phenomena of phosphorus reversion, which is not a problem during the initial stages of steel making. That point must be understood very clearly, okay, because the initial stages phosphorus is not removed also to a significant extent, because in the initial stage what happens is the phosphorus, it takes half a minute or so, then the phosphorus removal starts to occur in the system itself. Of course, you have large scale silicon oxidation, you have large scale heat generation, and as a result of which the lime starts to dissolve, and then because the basicity will develop, the first slag to form will still be FeOSiO2, okay, and then progressively lime will dissolve, lime will replace FeO. So to get to this particular value of 4, it will take some time. So during the period I am talking about, the basicity is developing, the temperature is not too high, and the slag is not too basic. In that case, what happens, despite you have oxygen, high oxygen potential, not significant amount of phosphorus removal. So halfway through, the phosphorus removal is quite rapid, but come to the later point, or the end point of the blow, and then there is a chance, and if you play your cards wrong, in that case what happens, you can land up with a huge temperature in the system, and as a result of which phosphorus reversion. So we have to be careful towards the end of the blow, particularly regarding, because our objective is to drive or eliminate phosphorus from steel. We do not want phosphorus to get back from slag to the metal, having successfully eliminated phosphorus. So that temperature control, and that is why the endpoint control is so important for us. Now you can see that if we cannot control the endpoint, we have a chance of not only hitting the wrong carbon, but also getting, phenomena like phosphorus reversion, or I would say that phosphorus elimination may not be that, effective if we particularly fail to hit the endpoint very precisely. We will study and discuss this endpoint control and how the steel plants strategize in terms of their endpoint control with the modern day machineries and sensors that will be discussed when we talk of process control in oxygen steel making processes. Now, so basics, this slag essentially indicates, the slag basically indicates that, this equation basically indicates that we have a basic slag, and just like the way, and the slag has some oxygen potential, it has, you can interpret that either in terms of dissolved oxygen or in terms of the FeO content of the slag. Just like the way we have used a terminology called the sulphide capacity, we can have for basic slag actually these capacities are very popularly used, and not only for basic slags, I would say for carbidic slag, we can say carbide capacity of the slag. Similarly, we have terminologies like water capacity of the slag. So, these are very important thermodynamic parameters, and you must understand that these definitions are by no means unique. I mean, for example, I have written one expression when I was talking about pretreatment sulfide capacity, which I have written in terms of an equilibrium constant into activity of the basicity, okay, or the ions divided by F(S2 minus) in the slag phase. This is the definition, and this definition, by the way, is not a unique definition. There are several definitions of what you call the capacities. Okay. For example, this is a popular definition, and another definition of sulfide capacity is, for example, I can say it is LSE, which is the equilibrium partition coefficient, and then we can say that this is what percentage oxygen, and this is I think -1 or something like that. So, I will check and correct it. Okay. So, which essentially tells us that this is one can also write this in terms of an aluminum kill steel, for example, in terms of what percentage aluminum raised to the power minus 0.66. This comes from the figure 0.66, because if you think of oxygen aluminum equilibrium Al2O3, so 2:3 proportion oxygen is to aluminum, and that is how this has come into the picture. So, this is another one definition of another definition of CS, this is another definition of CS. So, many people use different kind of definitions, and these are all correlated because these are derived on the basis of equilibrium considerations, since the states are fixed. So, one can transfer. It is just like you are having a meter scale against a foot scale. So, you can measure the length in foot, you can measure the length in meter, and then you have the conversion table. So, same is the case in the case of different definitions of the sulfur. It depends on your convenience which definition you want to use, but for us it is important to know that sulfide capacities are important parameter, and in this present context we will say a phosphide capacity is also an important parameter of the slag, which will tell us that how good the slag we have conditioned or we have made is for phosphorus absorption and so on and so forth. So, just like the way we have the phosphide capacity is represented in terms of LPE equilibrium into what percentage oxygen raised to the power minus this is LPE. So, the phosphide capacity is going to increase with increased oxygen content of the material. So, this is going to be is equal to 2.5, and that shows the different relationships here. You can see one is inversely proportional to oxygen, the other is directly proportional to oxygen, and then you can see that what is the power of, and this essentially tells that phosphide capacity is a strong function because the power is 2.5, not just 1, okay, on oxygen itself. So, this is a very popular definition of phosphide capacity, and the phosphide capacity I think in which this LPE I have already given the definition. LPE basically is equilibrium partition coefficient of phosphorus, and that is what percentage of phosphorus in the slag divided by what percentage of phosphorus in the metal. Okay. Now, we can have an LPE definition to express, as I have indicated, that equilibrium partition coefficient. On the basis of this equation, I said that it is going to be a function of equilibrium constant. Equilibrium constant is a function of temperature. It is going to be a function of the basicity parameter. It is going to be a function of oxygen. So, LPE is similarly expressed in terms of, I would say, log LPE. Okay, log LPE is equal to it is I think 9 minus this is T 21,000 approximately. These values again I would say somewhere you may find that it is 21,780, somewhere you will find it is 21,9,000. So, these are experimentally determined values. So, there is going to be some variation from source to source and a reasonable value, and if you want to apply, I think in your calculations a value of the equilibrium constant, I would suggest not to pick up the value from these lectures, because here only I am quoting a representative value. Okay? So, you have to consult the literature, the correct literature, see the band in which, and select for yourself from those archival references that what is a plausible value in your case. But for our discussion, it is sufficient to know, say, so I have written only an order of magnitude value. This is a reasonable approximation, and this is I think 9.87, okay, and this is the equilibrium constant part, and then we have 0.71, 0.7 into the parameter BO, which I am going to explain, and then this is going to be 2.5 times into what percentage oxygen. This is, so this exhibits the relationship, the dependence of equilibrium partition, that how much phosphorus ratio in this slag to phosphorus ratio in the metal. So, this is a component of the equilibrium constant, this is a component from the basicity parameter, and this is a component from the oxygen, which is consistent with this particular equilibrium representation of the dephosphorization reactions. Now, what is this parameter BO? BO is a basicity parameter, and the basicity is, so long as you define your parameters, there is absolutely no problem. One can have an equation. I have already shown you or told you that we have a V ratio or a basicity ratio, which is given in terms of the most simplistic one, which is very popularly used in industry. It is professors and researchers who would like to use, explore different kinds of definition. But if you go to the industry, you will find out that what percentage of oxygen, this is used as a basicity parameter. The Slag basicity is dictated by, this may not be an accurate, so it will vary from case to case, as we will also introduce other definitions of modified V ratio, etc., what people uses to characterize the basicity of slag. But in this particular context, the BO parameter is actually what percentage of calcium oxide, what percentage of no acetic oxide will come, because it is a basic oxide. So, it is a calcium fluoride, okay, which of course is not a very good compound, because the slag, if you are using for land filling, we must understand that fluorides is going to contaminate. So, there is a worldwide ban now on usage of calcium fluoride in steel making slags, because we are producing slags in huge tonnage, as I have indicated. In steel making itself, maybe 300 ton converter will give us something like 15% of slag by weight. So, therefore, this is not a desirable one, but this is the conventional definition of what do you call, and 3%, I think this is 0.03 into what percentage of magnesium. So, that is what is the definition of the BO parameter. It is a basicity parameter, and this tells us that we indeed, as the BO basicity is going to be increased, basicity parameter, so is going to be the LP value. So, the basicity parameter, yes, so it is going to be 0.3, I think, yes, that is what is the value. I have written it 0.03, so that is the value. So, this, if you represent in terms of a figure, then you can show that basically you have LPE, and please note this side is on a logarithmic scale, while this side is on a usual scale, okay. And then if you plot the BO parameter, and then you will find that the line goes something like this. So, if you have, then you have a second line here, and I can now tell that your understanding, what is your understanding, that if I say that this two line corresponds to two different temperature, then which one is at higher temperature and which one is at lower temperature? Because we said that at lower temperature and lower temperature, higher temperature, we are not talking about 100 degree, 200 degree, we are talking about either 1690 degree vis-a-vis 1600 degree centigrade. That is the definition of low and high temperature. So, if I have two different lines A and B, it is understood that LPE, higher partition coefficient, equilibrium partition coefficient is achievable at lower temperature. So, this line should correspond to a relatively. So, if I give you two temperature 1600 versus 1690 and label these two lines, you would label this to be 1600 and this line to be 1690, because you have a lower partition coefficient for a given value of BO. Okay. For the same value of BO, if you go here, I get a higher temperature. So, this must be a low temperature relatively LT, and this must be the line at higher temperature. So, this is the schematic variation, and people have done a lot of experiments and they have found out also that it is possible, this kind of a relationship exists, and it is indeed possible that you increase basicity to a very large value like 4 etc., which is only possible in basic oxygen steel making process. Even in pneumatic steel making process, even in a hearth steel making, no other steel making process, such large V ratio is possible. It is here only because of you are using pure oxygen, and that you have an intense metalloid, and if you have the correct silicon content of the hot metal, you can have sufficient amount of heat which will help you to produce. Now, one important thing is that the iron oxide content of the slag has a very important, this discussion is incomplete so long as, so you tend to believe by now that, as Sir has indicated, that as you increase oxygen in the melt, and as I said, as dissolved oxygen in the metal is going to go up, and I say that phosphorus in the slag is going to go down, and this essentially means that if dissolved oxygen goes up, the FeO content of the slag will also go up. Okay? So, I would say as oxygen content of the melt goes up, increases, you can get good phosphorus removal or large equilibrium partition coefficient. Alternatively, I can say if the slag contains large is one and the same statements, said in a different way. If the slag contains or the slag oxygen potential is higher, the slag contains large amount of FeO, in that case also it is you can get good value of LPE, you can get quite high value of phosphorus in the slag itself. But this is not applicable across the entire range. I do not mean to say that it's monotonically is going to increase. That is not the case, and I will explain that why it is so. So, basically it is seen that with the content of iron oxide in the slag, okay, if you say that we have P2O5, weight percent P2O5 in slag divided by weight percent P in metal, then it is seen that this value goes up and attains some sort of a maximum value around 15 weight percentage of FeO, and then what happens is that similarly, if I draw these two lines and I try to tell you to label that these are applicable to two different basicity values, okay? One is high basicity, one is 4, other one is 2. How you are going to label it? Because you apply your fundamentals now, higher the basicity, more the dephosphorization. So, therefore, this line must correspond to V is equal to 4 as I have indicated. These are schematic representations, not exact, I have not labeled the scale for example, and this must be V is equal to 2. But what it tells us that after about 15% FeO, if you increase the oxygen in the bath, okay, you will see phosphorus is not increasing, and indeed the phosphorus has started to decrease in the system. So, phosphorus has now started to come back to the metal itself. Why it is happening? And to understand and appreciate this graph, you have to understand the kinetics of slag formation and how does the lime really gets dissolved in the slag. That needs to be understood clearly. So, basicity initially we must understand, we will talk about this later in greater detail later on. We have the slag that forms as I have indicated. The moment you start putting in oxygen, because of the large affinity of silicon towards oxygen, you will get instantaneous formation of silicon, spontaneous oxidation of silicon, and rapid oxidation of silicon to silica will take place. Similarly, iron being the bulk of the 95% being iron of the melt, iron oxide, and this is very easily we have seen in the blast furnace in the cohesive zone the first slag to appear at relatively low temperature so at relatively low temperature this is the slag phase that is going to be generating. Now, onto this you are adding lime. In steel making you do not add limestone, you add lime. So, let us look at the lime particle, which is, this is my lime particle, you have added, okay. And this lime particle, these are all, this is an oxide phase silicate and this is CaO, they are both much lighter than that of molten hot metal. Okay. So, they are going to be remaining at the surface of the steel. So, it is typical scenario is going to be like this. If the surface is like this, the FeO is going to be here, FeOSiO2, and when you add silica, this CaO particles are going to be really floating here rather than going inside the melt. So, this is my melt phase, okay, or the hot metal, and then this is the slag phase, and this is what is the scenario somewhere around the initial period of slag formation and lime addition. The moment you add lime, what happens is this iron silicate starts to react with lime. And this reaction, this is a liquid and this is a solid. This is a solid liquid chemical reaction. So, the rate we expect is not going to be too fast. Okay? Liquid reactions are fast, gas liquid reactions are fast, solid liquid reactions are relatively slow, but at least it is better than solid reactions, that is what we understand. Okay? And as a result of which, what happens is the reaction takes place and we have a phase which forms as calcium. This phase is called calcioustite. Although I write FeO, we know that oustite is Fe0947O from our knowledge of iron making. And then we have dicalcium silicate, CaO SiO2. Okay, that is what it is. So, 2 silicate we have. So, we have calcium oxide. So, we have 2 calcium oxide and 2 silicates. So, we can balance it also, there is no problem. 2 calcium oxide, 2 FeO. So, Ca2SiO3. So, that is what it is. Yeah, that is fine. So, you can have here, I think. So, you can adjust it, 2 FeO, 2 FeO, 2 SiO2, 2 SiO2, okay, that is fine. Dicalcium silicate. So, you can write it, I think, CO, 2CO. This is 2CO. So, we have 2 FeO, SiO2. So, that is fine. So, this is this, and that is dicalcium. I think I should write it like Ca2, 2 calcium oxide. So, Ca2, this is dicalcium silicate, calcium oxide SiO2, that is what. So, this is, then of course, the reaction is not balanced. Okay. I will check book and then I will write these reactions later on. So, let us put it like this. So, if you do this, in that case what happens is when lime comes here and it is immersed or it is dropped in this vessel, and so it is surrounded by calcium silicate. So, we have calcium silicate which is there around the lime particle, that is the calcium silicate. and now the reactions takes place. And what does the reaction takes place? The reaction will take place at the solid liquid interface, and at this particular reaction what happens is the first, and this is what, this is, I think you will complete, this is the liquid phase and this is the solid phase. So the solid forms, calcium osteite is liquid and this is solid. So the dicalcium silicate will precipitate out as fine powders from the liquid, and this is going to be, these are the precipitates of dicalcium silicate on the surface, which is surrounded by a calcium osteite. So the entire, because of this reaction, what happens is that the the further lime dissolution is going to be not possible. This lime is, so much of lime is there, and this lime is now completely surrounded by another solid particle, solid which we call as a dicalcium silicate. So the lime is not really capable of for that this precipitates here, which are surrounded by the liquid calcium osteite, which forms the product, and within that particular liquid. So this is the this basically is the product that has generated, and this product possibly you can see to be a liquid in which the solid particles are dispersed, okay, and this provides some kind of a impervious coating around the existing lime body, allowing or impeding the further dissolution rate of lime itself. So the lime is unable to dissolve into the slag, okay, and as a result of which what happens is the basicity does not increase beyond a substantial level, and once the basicity is not able to increase, and this basically happens because of the formation of dicalcium silicate. So we have to go to a scenario where we can prevent. There are other silicates also which can form. It is not necessarily that dicalcium silicate will always form. This is one of the possibilities. We will see that when we talk about the slag chemistry and the ternary phase diagrams. There are, if you can control your temperature, you can control your composition, etc., very correctly, in that case it is possible that you can generate a liquid here. The moment you generate liquid, the liquid is going to be separated from the solid because of the agitation which is present there. But this solid, the moment you form solid here, this solid will have a tendency to already existing sinter with the already existing solid, and as a result of which an impervious coating may be generated around the lime itself. But if we can somehow tailor make our composition such that the resultant reaction gives us a liquid phase, then the lime is always going to be exposed to the liquid, and the progressive dissolution of lime will take place, making the slag more and more basic. So therefore, it is understood that we have, if you have more and more FeO in the system, and then formation of this will take place, and as a result of which higher is the concentration of FeO-SiO2, then greater will be the difficulty in lime dissolution. So if this product does not exist, then there is no problem at all, okay. The lime will progressively dissolve, and then it will form silicates, calcium silicates, and so on and so forth. So that is not going to be an issue, but the more is the concentration of FeO in the system or FeO-SiO2, in the chances of lime dissolution in the presence of a large iron silicate slag is going to be greatly hampered, and as a result of which what happens, we can, and this phenomena, that's what it says, that when you have 5%, 10%, you do not see this phenomena, because you have the lime is, progressive dissolution of lime is still not that impeded, but once you cross 15%, in that case really the dissolution of lime is going to be a big, it is not exposed to the surrounding slag into which the lime can go in, okay. So therefore, and you can see that we were targeting a basicity of about 4, okay. So therefore, it is not for every I mean, if you say x wet percentage of SiO2, we are aiming at 4x wet percentage in the slag itself. So the lime remains in the dissolved state, and that dissolution is not going to be possible if it is coated by a material which is solid and which has gotten sintered with the lime surface itself, okay. And that we will discuss this later on when we talk about what we call the slag making during oxygen still making process. So as a result of such, we can expect that as the lime content, as the FeO content increases, there will be. So, this is a wet percentage 15% essentially tells us that we have now enough FeO in the system to impede the dissolution rate of lime, and as a result of which and this also tells us that towards the end part, when the process is ending or the carbon content has come down and we are blowing, that at that point there is a chance of the slag FeO builds up very rapidly. I have been telling it repeatedly because this is very important. And so, a high FeO content of the slag coupled with high temperature which is generated towards the end of the blow are essentially the reason for rephosphorization of the hot metal or phosphorus reversion from slag to metal. So, therefore, the endpoint control has been given so much of emphasis in modern day steel making, such that there is not excess amount of FeO. Controlling FeO in the slag is a great art as far as oxygen steel making is concerned, and this will to a large extent give rise to the correct kind of a temperature towards the end of the blow. So, hitting correct FeO content in the slag, hitting correct carbon composition, hitting correct bath temperature is not by an easy task, and you cannot just do it by experiments or trials, and you have to have modern machineries as well as sensors in order to guide you, so that you can arrive at the end point precisely. So, we can now, so we have discussed all the 5 reactions. So, these 5 reactions basically we have carbon oxygen reaction, that is what we have discussed. We have also discussed silicon oxygen reactions, we have discussed manganese oxygen reaction, not much sulfur reaction also we have covered in the context of blast furnace and steel making and pretreatment, and we have also covered phosphorus reactions. So, all the 5 important reactions have been covered. So, therefore, there is no problem as far as this is concerned, and we can also say here that all these reactions, as I have indicated, at elevated temperature and under steel making conditions are feasible to a different degree. While phosphorus, silicon, carbon will oxidize very rapidly, sulfur will not get eliminated very rapidly, as I have indicated. Now, let us look at having said so much about the equilibrium and the chemical nature of the chemical reactions, let us look at that if these reactions are feasible, let us answer one question, that at what rate the reactions are going to occur, and for that we have to understand that the kinetics of steel making reaction. So, steel making reactions, as I have indicated, they are either gas metal type reactions and number 2 slag metal type reactions. Multiphase chemical reactions are a characteristic of steel making process. Okay? Gas metal reaction, the example is that yes, O2 to dissolve O, reacting with FeO, Fe, and then producing the entire sequence of reactions. Slag metal reaction, we have seen one such reaction is these reactions. You must understand that all these reactions, that is because they are heterogeneous reactions, okay, we are talking about multiphase reactions, gas metal, slag metal. So, they occur at phase boundary and they are therefore, that is the site of the reaction. Just like the way I have mentioned here, that is a liquid solid reaction, this was our FeO SiO2, and this is the lime particle, and the lime and SiO2, this reaction, chemical reaction as I have indicated, takes place at the interface, which is this line, solid liquid interface. That is the line at which the reaction takes place. So are these reactions at the boundary of gas and metal, common interface at the boundary of slag and metal, these reactions are going to take place. If the reactions takes place at the boundary, it must be understood that since systems are multi-component systems, slag is not just CaO, the slag will contain CaO, SiO2, sulfur, phosphorus, MgO, etc. So, the interface, if there is a reaction of CaO with sulfur, then I must say that at the phase boundary, the CaO must be available. CaO is there everywhere in the slag itself, but it is not pure CaO, that is what you must understand. So, such reactions can take place provided the anion, or which is the measure of CaO, can transfer to the slag metal interface. Suppose if you say that this is our slag metal interface, SM interface, and this is slag and this is metal, and this contains CaO, SiO2, MgO, FeO. The reaction can only take place provided the CaO is available at the interface. You must understand, as the reaction is going to take place at the interface, CaO is going to be consuming. Okay? There will be no CaO left after some time. So, a continuous transfer of CaO from the slag to the interface is necessary in order to drive this reaction in the forward direction. So, although you see it as a chemical reaction, you must understand that hidden in this chemical reaction are transport steps. The species needs to be transported to the interface, and then only the reaction is taking place. Similarly, sulfur is here. The moment the sulfur is transferred here, the reaction will take place, then there is no sulfur. So, the reaction will come to stop. So, there needs to be a continuous transfer of sulfur from the bulk of steel to the interface itself, such that the chemical reaction. So, calcium oxide will transfer from slag to the interface, sulfur will transfer from bulk of metal to the interface, then they will react, then the rearrangement of bond is going to take place, and then we will see a pure chemical reaction between sulfur and CaO right at the slag metal interface. So, therefore, per se this chemical reaction, okay, or the desulfurization reaction, I would say, the desulfurization reaction will consist of several mass transfer steps and one single reaction at the interface itself. Similarly, we want, once the product forms, the product has to be moved in different direction. Otherwise, if the product accumulates here, the reaction will come to a stop, it will go in the reverse direction. So, whatever the product which is being generated, which is shown by yellow arrows on the board, the product has to go in the reverse direction, and as they are making room for fresh CaO to come to the interface to the reaction site, fresh sulfur to come to the reaction site. So, these 4 arrows basically represent the 4 mass transfer steps for this particular chemical reaction. So, overall I would say that the desulfurization process in steel making can be represented in terms of 4 mass transfer steps and 1 chemical reaction steps. So, I would say there are 5 independent kinetic steps which comprise or which constitute the desulfurization process, and all these processes work in series. If you stop one of them, the entire process of desulfurization will come to a standstill. So, they work in series, and if they work in series, their rates are going to be determining, individual rates of these steps will determine the overall rates of the desulfurization process. If the calcium oxide movement is too slow, then even though everything else is there, sulfur is there, conditions are there for product can be moved, but since the arrival of calcium oxide itself is very slow, the reaction is going to be very slow. Okay? So, therefore, we can conclude that the individual rates of these kinetic steps 1, 2, 3 and 4 and 5 when summed up will give you the total rate of the desulfurization process. Now, obviously under many conditions, still making conditions, because the temperature is very high and that rate of chemical reaction obeys an Arrhenius type of rate law, where it is the T term, the temperature term is engulfed in the exponential. So, at high temperature the contribution of the exponential term is very large. So, barring few exceptions, we would say that the rate of the chemical reactions, the moment the reactants are available, they will rearrange the bond in no time and take the reaction to completion. Sulfur will reach there and immediately calcium sulfide will form and go to the slag phase, because the temperature is very, very high. So, therefore, the rate of this process is going to be very, very slow in general. There are exceptions of course, when rate of the chemical reaction may not be that slow, particularly when complex etc. forms or surface etc. are blocked by a poisoning elements and so on and so forth. So, as a thumb rule you can say then steel making conditions, these mass transfer steps tend to be slow in comparison to the chemical reaction steps, and that is why we have been saying all the time that we need stirring. I have made that statement categorically, that why open hearth process took such a long time for refining, because in the open hearth process, conventional open hearth process, there was no good agitation, and we see that if chemical reactions are not rate limiting, mass transfer determines the rate of the process. So, therefore, the rate of dephosphorization, the rate of carbon oxygen reaction, they are going to be dependent on mass transfer, and the transport of species from one point to another point is a function of the stirring condition. If you do not have stirring, you will not have good rate. For example, if you make your morning tea, add sugar, do not forget to stir the contents in the cup, then what is going to happen? The sugar is not going to dissolve. You will finish the tea thinking that you have not added any sugar, and the sugar is going to be found settled at the bottom of the vessel itself. But the moment you use a stirrer, stir the contents in the cup, the sugar gets dissolved, and this is precisely the reason that stirring expedites mass transfer, stirring expedites dissolution and so on and so forth. So, therefore, stirring is a very important part of the metallurgical process, and all these steel making processes in liquid stage, we will see in some form or other we will be giving stirring, because all our chemical reactions, heat and mass transfer processes tends to be transport controlled, where the transport tends to play a dominant role. Okay? So, having said that, so therefore, I can now say go inside the process. The transport in the slag phase could also be slow. I am trying to make my life simple, that I have 4 steps to deal with. Can I simplify the scenario? So, transport in the slag could be slow, or transport in the melt phase could also be slow, and we all know that there are boundary layers on both sides of the slag metal interfaces from our knowledge of mass transfer theories, and often we find that transport across the boundary layer is slow and not the transport in the bulk, because the bulk tends to be very, very well agitated. So, therefore, the kinetics of the reaction can be, or the rate of the reactions or desulfurization, rate of oxygen dissolution, rate of other slag metal reactions can be characterized in terms of mostly the resistances offered in the transport across the boundary layer, and we say that for example, statements like this you will come across, that melt phase transport of sulfur is assumed to be the rate limiting step, which essentially indicates that the transfer of sulfur from the bulk to the interface is rate limiting, or I would say from actually, because the bath is starred across the edge of the boundary layer, is important. We will continue with this discussion during the next lecture. I will check